A colossal void in space defies gravity itself. This is not science fiction, but a staggering reality astronomers have mapped. We are talking about regions so empty, they challenge the fundamental force that holds our universe together. In the constellation of Boötes, scientists found a cosmic desert so vast it could swallow thousands of galaxies, yet it remains almost perfectly barren. How can such immense nothingness exist, and why does it seem to push matter away, as if gravity is working in reverse? By the end of this exploration, you will understand the true, mind-bending nature of these voids and how they are reshaping modern cosmology. We will uncover the detective story behind their discovery, from the eerie cold spots in the universe's oldest light to the mysterious influence of dark energy. What does such profound emptiness reveal about our place in the cosmos? This intricate architecture is the universe's true skeleton. For decades, astronomers saw the cosmos as a fairly uniform collection of galaxies scattered randomly across the dark. But with increasingly powerful telescopes and sophisticated sky surveys, a breathtaking pattern emerged. We now see that galaxies are not scattered at all. They are woven together into a colossal, three-dimensional tapestry of light and shadow, a structure so immense it defies human comprehension. We call this the cosmic web. Its threads are long, delicate filaments of thousands of galaxies, streaming across the emptiness like rivers of stars. These filaments connect at dense, bustling intersections known as galaxy clusters, the great metropolises of the cosmos where thousands of galaxies swarm together. And surrounding and separating all this luminous structure are the voids. These are the true backcountry of the universe, the immense, silent spaces between the threads and knots of the web. To call them empty is an understatement. A typical void can stretch for over 100 million light-years, a volume of space so vast it could contain our entire local group of galaxies with room to spare, and yet it may hold only a handful of small, isolated galaxies. The contrast is staggering. It is the difference between a vibrant, neon-lit city and the deep, silent expanse of the open ocean. This cosmic sponge structure did not appear by accident. Its origins are written in the first moments of time. In the fiery aftermath of the Big Bang, the newborn universe was not perfectly smooth. Tiny, quantum ripples in density, smaller than a single atom, were imprinted upon the fabric of space-time. For billions of years, gravity acted as the universe's great sculptor. It patiently worked on those tiny imperfections, pulling ever so slightly more matter toward the slightly denser regions. Over cosmic epochs, this gentle tug became an irresistible force. The dense spots grew into the seeds of galaxy clusters, while the matter between them slowly drained away, flowing toward the growing structures. The voids are what remained after this great cosmic drainage. They are the footprints of gravity's constructive work elsewhere, the negative space that defines the positive image. But here lies the first hint of the mystery. If gravity only pulls matter together, why are these voids so exceptionally, profoundly empty? Why hasn't some residual matter fallen back in? The very existence of these vast, stable deserts suggests that within them, the rules of the gravitational game might be different. The year was 1981, and a team of astronomers was conducting a routine survey of the northern sky. Their target was the constellation of Boötes, the herdsman, a region they expected to be rich with distant galaxies. But as their data came in, a profound and unsettling silence emerged. Where their instruments should have registered the faint glow of thousands of galactic cities, they found only a handful of dim, lonely points of light. They had not discovered a new structure, but the absence of one. They had mapped a hole in the universe. This was the Boötes Void, a spherical region of space roughly 330 million light-years in diameter. To grasp that scale, imagine a bubble so large that if you placed our Milky Way at one edge, the other side would be farther than the distance to the great Andromeda Galaxy multiplied by 10,000. Within that incomprehensible volume, only about 60 galaxies have been found. In a typical region of space that size, you would expect to find not 60, but several thousand. The initial reaction was one of disbelief, followed by a deep scientific shock. This was not a small gap or a minor irregularity. It was a colossal cosmic desert, a great nothing that defied the standard understanding of how matter should be distributed. The universe, according to the prevailing models of the time, was supposed to be fairly smooth on the largest scales. Yes, there were clusters and groups, but they were thought to be embedded in a more homogeneous sea of galaxies. The Boötes Void shattered that assumption. It revealed a cosmos that was startlingly lumpy, structured not just by where matter was, but by where it emphatically was not. The void was not empty because galaxies had never formed there. The evidence suggested something more dynamic. It appeared that over billions of years, the gentle pull of gravity from the surrounding denser regions had slowly siphoned away the gas and galaxies that once called this place home, leaving behind a drained and isolated pocket. But this explanation immediately raised a new and more troubling question. If gravity only attracts, why did this process create such a perfectly clean evacuation? Why wasn't the void littered with the stragglers and leftovers of that great migration? The pristine emptiness of the Boötes Void hinted that within its borders the force we thought we understood might be behaving in a way no one had anticipated. This discovery forced cosmology to grow up. It could no longer be the study of matter alone. It had to become the study of emptiness as an active, shaping component of the cosmic architecture. The hunt was on to find out what rule, or what missing piece of physics, governed the silent expanses between the threads of light. The Boötes Void was not just an empty room in the cosmic mansion. It was a room that seemed to have its own strange weather. As astronomers studied the few galaxies clinging to its edges, they noticed something that defied simple explanation. These galaxies appeared to be moving in a way that suggested they were being gently pushed away from the void's center, as if the emptiness itself was repelling them. This was the gravitational enigma, a phenomenon that, on the surface, looked like gravity working backward. For centuries, from Newton to Einstein, our understanding has been built on one unshakable pillar: mass attracts mass. Gravity is the great gatherer, the force that pulls things together to form planets, stars, and galaxies. The idea that a region of profound nothingness could somehow push matter away seemed to violate the most fundamental rule of the cosmos. Yet the evidence was there, written in the subtle red shifts and trajectories of those lonely border galaxies. The key to unraveling this illusion lies not in rewriting the laws of physics, but in understanding the delicate balance of forces on the largest scales imaginable. Think of it not as a simple tug of war, but as a complex dance set to the accelerating rhythm of the universe itself. Imagine you are a single galaxy located near the boundary of one of these colossal voids. Behind you, stretching for hundreds of millions of light years, is the dense, matter-rich wall of the cosmic web, a gravitational anchor of immense collective pull. Ahead of you lies the void, an expanse of such profound underdensity it is almost a perfect vacuum. According to Einstein, gravity is the curvature of spacetime caused by mass and energy. The dense wall curves spacetime sharply toward it, creating a strong gravitational well. The void, with its lack of mass, creates almost no curvature at all. It is like a flat, featureless plane. So as you, the galaxy, sit on this cosmic slope, you naturally feel a stronger pull from the massive wall behind you than from the empty plane ahead. The net effect is not a push from the void, but a stronger pull from everything that is not the void. You are being drawn toward the dense regions, which makes it appear as if you are being repelled by the empty ones. This is the first layer of the illusion, a simple matter of gravitational contrast. But there is a second, even more powerful actor on this stage, the overall expansion of the universe, fueled by the mysterious dark energy. Within the dense filaments and clusters, gravity is strong enough to hold galaxies together locally, fighting the global expansion. Inside a void, however, there is almost no gravity to provide that counterbalance. Here, dark energy's push has less competition. This means the void itself is expanding faster than the universe's average rate. So a galaxy at the edge is not only being pulled toward the wall, it is also standing next to a region of space that is stretching outward more aggressively. The combined effect creates that unmistakable signature of apparent repulsion. The void is not pushing matter away, gravity is still pulling as always. Instead, the emptiness allows the background expansion of space, supercharged by dark energy, to express itself more freely. This subtle dynamic reveals a profound truth. On the grandest scales, gravity and cosmic expansion are locked in a continuous, delicate duel. The colossal voids are not passive holes, they are active participants in this struggle, their very emptiness amplifying one of the universe's most mysterious forces. This subtle gravitational illusion was just the beginning. To find the true, physical signature of these voids, astronomers had to look not at the galaxies around them, but at the oldest light in the universe itself. The cosmic microwave background is the faint afterglow of the Big Bang, a snapshot of the infant cosmos when it was just 380,000 years old. This light has been traveling for over 13 billion years to reach us, and its journey is not a simple one. As these ancient photons race across the cosmos, they pass through every structure in their path, including the colossal voids. And when they do, something remarkable happens, an effect predicted decades ago but only recently confirmed. It is called the Integrated Sachs-Wolfe effect. The name is complex, but the concept reveals a beautiful cosmic interaction. Think of a CMB photon as a tiny marble rolling across a vast, undulating landscape. The hills and valleys of this landscape are the gravitational potentials created by the cosmic web, dense clusters creating deep wells and empty voids creating shallow, flat regions. As the universe expands, these gravitational landscapes change. The deep wells of clusters become slightly shallower over time, and the gentle dips of voids become even flatter. Now imagine our marble, the photon, enters a supervoid. As it rolls into this region, it is descending a very gentle slope, but by the time it is ready to roll out the other side, billions of years have passed. Because the void has been expanding and emptying out further, the slope it must climb to escape has become even more gentle than when it entered. Climbing a shallower hill requires less energy. In the world of light, less energy lost means the photon retains more of its original strength. To our telescopes, this translates to a tiny, specific patch of the microwave background appearing ever so slightly warmer or hotter than the average. Conversely, a photon passing through a dense cluster would lose more energy climbing out of a deepening well, appearing slightly colder. These minute temperature fluctuations are the cosmic shadows, the direct fingerprints of structures imprinted on the primordial light. The detection of this effect, particularly linked to known supervoids, was a watershed moment. It provided observational proof that these vast, empty spaces are not static. They are dynamic, evolving entities whose gravitational influence is actively changing over cosmic time. More importantly, the strength of this shadow effect is a direct probe of dark energy. In a universe without dark energy's accelerating push, the gravitational landscapes would not evolve in this specific way. The fact that we see these telltale hot and cold spots in the CMB, aligned with the locations of voids and clusters, is some of the strongest evidence we have that dark energy is real and is shaping the cosmos on the grandest scales. The silence of the void, it turns out, speaks volumes. It whispers its story in a language of subtle temperature shifts, a message from the emptiness that helps us decode the fate of everything. Mapping these silent voids is an art of cosmic subtraction. You cannot point a telescope at nothing and expect to see it. Instead, astronomers must chart the light, then carefully define the profound darkness that lies between. This monumental task has been made possible by projects like the Sloan Digital Sky Survey, a dedicated telescope that for years systematically scanned the heavens, cataloging the precise positions and distances of millions upon millions of galaxies. Imagine trying to map every city and town on Earth from space, then using their locations to outline the shapes of the oceans and the vast deserts. That is essentially what cosmologists do. They feed the three-dimensional coordinates of all these galaxies into powerful computers, which then run sophisticated algorithms designed to find the largest possible spheres that contain virtually no bright galactic cities. The result is not a single snapshot, but a statistical portrait of the universe's anatomy. These three-dimensional maps reveal the cosmic web in stunning detail, with luminous filaments twisting around cavernous spherical voids. Each void is catalogued by its size, its shape, and the sharpness of its boundaries. Some are nearly perfect bubbles of emptiness, while others are more irregular, like the rooms in a complex sponge. This data is far more than a pretty picture. It is the essential raw material for testing our deepest theories. By measuring how many voids exist at different cosmic epochs, and how their sizes and distributions change over time, scientists can perform a rigorous check on our models of gravity, dark matter, and dark energy. Does the pattern of emptiness match what Einstein's theory predicts when dark energy is added? Or do the voids grow and evolve in a way that hints at something new, a subtle crack in our foundational physics? The emptiness, meticulously mapped, becomes a laboratory. It is a silent, expansive stage upon which the most fundamental forces of the cosmos play out their roles across billions of years. But this cosmic tug-of-war has a silent, dominant partner. To truly grasp why the void seems to push, we must confront the universe's greatest mystery, dark energy. This is not a substance you can touch or see. It is a property of space itself, a kind of latent energy woven into the fabric of the cosmos. Its primary effect is a gentle, relentless pressure that causes the expansion of the universe to accelerate over time. On the grandest scales, dark energy behaves like a form of anti-gravity, not by repelling matter directly, but by causing the very space between galaxies to stretch at an ever-increasing rate. Now picture that delicate balance of forces again. In the dense, crowded neighborhoods of galaxy clusters, gravity is king. Its powerful local grip holds galaxies together, fighting against the background expansion driven by dark energy. It is a stalemate, with gravity winning the local battle, but step into a colossal void. Here, the gravitational anchor is almost non-existent. There is simply not enough matter to put up a meaningful fight. In this near-perfect vacuum, dark energy encounters little resistance. The void, therefore, does not just expand with the universe, it expands slightly faster. The space within the void stretches more aggressively than the space within the crowded filaments. This is the crucial insight. A galaxy at the edge of this emptiness is not being magically repelled. Instead, it is sitting beside a region of space that is inflating like a balloon that is being blown up a bit quicker than its surroundings. The galaxy itself feels the stronger pull from the dense wall behind it, while the void floor ahead is literally being pulled out from under it by this enhanced expansion. The combined effect creates that unmistakable illusion of a push. The void is not shoving matter away, it is simply getting emptier faster, because the dominant force within it has no competition. This transforms our understanding of these empty regions. They are not just passive absences, they are amplifiers. They magnify the effects of dark energy, making it possible for us to observe its subtle influence on the structure of the cosmos. By studying the size, shape, and growth rate of these vast cosmic bubbles, astronomers can take the measure of dark energy itself. The silence of the void, therefore, is not empty. It is filled with the faint signature of the force that will ultimately decide the fate of everything. The galaxies clinging to the edges of these voids are telling us a secret in their motion. Astronomers call it a peculiar velocity, a term that sounds almost whimsical but describes a profound deviation. Every galaxy is carried along by the overall expansion of the universe, a smooth, predictable flow known as the Hubble flow. But the galaxies bordering colossal voids are doing something more. Their motion contains an extra component, a subtle drift that makes them stream systematically away from the void's center, as if fleeing the emptiness. This is not a random twitch, it is a coherent flow, a silent river of stars moving against the cosmic current. To measure this, scientists must perform a feat of cosmic accounting. First, they calculate how fast a galaxy should be moving based solely on the universe's expansion and its distance from us. Then, using the light from specific stars or gas clouds within that galaxy, they measure its actual velocity. The difference between the predicted flow and the observed motion is the peculiar velocity, the fingerprint of local gravitational influences. For border galaxies, that fingerprint consistently points outward, away from the void. This presents a serious challenge to simple models. If gravity only comes from the mass we can see, the collective pull of the sparse galaxies inside the void would be negligible, far too weak to explain this organized outward streaming. The observed velocities are too high, so what is providing the extra push? The answer returns us to the concept of contrast, but now viewed through the lens of motion. The void is not just empty, it is a region of significantly lower density than the universe's average. Conversely, the surrounding filaments and walls are regions of higher than average density. In the framework of general relativity, it is this imbalance that matters. A galaxy on the boundary feels the gravitational pull from the massive wall behind it much more strongly than any feeble tug from the near vacuum ahead. The net force is a powerful pull toward the dense structure, which, from our perspective, looks exactly like a push away from the void. This dynamic reveals the voids as active sculptors, not passive holes. Their evolution is written in these velocity flows. As a void grows over billions of years, drained by the gravitational attraction of its surroundings, the border galaxies are swept along in this great migration. Their peculiar velocities are a direct measure of the void's growth rate, a speedometer for emptiness. This gives astronomers a revolutionary tool, a way to weigh the void by its effect. Since the strength of the outward flow depends on the total mass difference between the dense walls and the empty interior, measuring these velocities allows scientists to map the distribution of all matter, visible and dark. The dark matter, which does not emit light but exerts gravity, piles up in the same dense regions as the visible galaxies. Therefore, the peculiar velocities of border galaxies are not just tracing the emptiness, they are tracing the invisible scaffolding of the cosmos itself. By reading this subtle motion, we can begin to chart the unseen architecture that dictates where emptiness will form and how it will shape the universe's future. The peculiar motion of border galaxies gives us a snapshot of the void's present, but to understand its origin we must rewind the cosmic clock. How does a universe that begins in a searing, nearly uniform fireball evolve into a landscape of such stark contrast, where bubbles of near-nothingness stretch for hundreds of millions of light years? The answer is not found in our telescopes alone, but inside the humming chambers of the world's most powerful supercomputers. These are the digital universes, vast simulations where scientists can watch the birth of emptiness unfold from first principles. The recipe begins with a simple, almost featureless starting point, a digital representation of the infant cosmos just after the Big Bang. It is filled with a smooth, soupy sea of dark matter and a sprinkling of normal matter, imprinted with those tiny quantum ripples we detected in the cosmic microwave background. With the initial conditions set, the scientists press start. Then they let gravity do its work. The simulation runs not for days or weeks, but for the equivalent of over 13 billion years, compressed into a few months of processing time. Trillions of digital particles, each representing a clump of dark matter many times the mass of our galaxy, begin their slow cosmic dance. The force is simple attraction. But the outcome is breathtakingly complex. As the simulation progresses, those tiny initial ripples become the seeds of destiny. Regions that began with just a fraction more density than their neighbors exert a slightly stronger gravitational pull. Over millions of simulated years, they attract more and more matter from their surroundings. Like water draining toward a low spot, the digital universe begins to organize itself. Threads of matter condense into filaments, knots form at their intersections, and the spaces between them start to widen. This is the critical moment. Those initial regions that were slightly emptier than average, the underdense patches, experience the opposite fate. With less gravitational pull to hold onto their matter, they lose it. The particles within them are siphoned away by the growing attractors nearby. As matter leaves, these regions expand faster than the cosmic average, becoming even emptier, which in turn makes them lose matter even more easily. It is a runaway process of evacuation. What begins as a minor dimple in the density of the early universe over billions of simulated years inflates into a colossal spherical void. The supercomputers show us that voids are not accidents. They are the inevitable shadows cast by the construction of the cosmic web. Their vast sizes and spherical shapes are a direct result of this gravitational drainage operating in all directions. Most powerfully, when the simulations finish their run, scientists can compare their digital universe to the maps from the Sloan Digital Sky Survey. The match is astonishing. The number of voids, their distribution, their typical sizes, all align with what we observe in the real cosmos. This agreement is a monumental validation. It tells us that our understanding of gravity, dark matter, and the initial conditions of the universe is fundamentally correct. The voids are a natural prediction, not a puzzling anomaly. They are the cosmic negative space carved out by the same simple, relentless force that builds the galaxies. In these digital realms, we witness the birth certificate of emptiness, signed by gravity and dark matter, and it matches the one we hold in our observations of the real sky. The profound emptiness of a supervoid presents a direct challenge to our understanding of the cosmos. When the standard rules seem to bend, science must ask a fundamental question: are we seeing the effects of unknown components, or are the rules themselves wrong? This is the heart of a fierce and fascinating debate in modern cosmology, a debate where these colossal voids serve as the ultimate testing ground. On one side, there are theories that propose a radical rewrite of physics. Modified Newtonian dynamics, often called MND, suggests that our understanding of gravity, as defined by Newton and refined by Einstein, is incomplete. In regions of extremely weak gravitational fields, like the near-perfect vacuum inside a giant void, the force of gravity might follow a different mathematical rule. Proponents argue that the strange motions of border galaxies and the apparent repulsion could be explained not by dark matter or dark energy, but by a subtle change in how gravity itself operates when matter is scarce. It is an elegant idea, solving several cosmic puzzles with a single adjustment to a fundamental law. The opposing view held by the majority of cosmologists is the standard model of cosmology, known as the Lambda-CDM model. This framework is built on two pillars: Einstein's theory of general relativity, which has passed every test thrown at it for over a century, and the existence of two mysterious entities, dark energy, represented by lambda, and cold dark matter, the CDM. In this view, gravity is not broken. The bizarre phenomena are not caused by a change in the rules, but by the unique conditions the rules create. The model argues that the void's emptiness, combined with the relentless push of dark energy and the gravitational pull of the surrounding dark matter-rich walls, perfectly produces all the observed effects, from the peculiar velocities to the shadows in the cosmic microwave background. The voids in this framework are not evidence against Einstein, but a spectacular demonstration of his theory operating in its most extreme environment. This is not merely an academic disagreement. It is a struggle to interpret the universe's most silent places. Every new, precise measurement of a void's size, the flow of its border galaxies, or the temperature of the CMB light that passes through it, acts as a vote for one side or the other. So far, the Lambda-CDM model, with its dark components, has successfully predicted what we see. But the search continues, because if a void ever reveals a signature that this standard model cannot explain, it would not just be a discovery, it would be a revolution, forcing us to rewrite the textbooks on the most fundamental force in the universe. Gravity's lens works both ways. We are familiar with the breathtaking power of a massive galaxy cluster to warp the fabric of spacetime so severely that it acts as a natural telescope. The cluster's immense gravity bends the light from galaxies far behind it, creating stretched arcs and multiple images, magnifying the distant cosmos for our view. This phenomenon is a cornerstone of Einstein's theory. But what happens when the lens is not an overstuffed metropolis of matter, but a cavernous expanse of nothing? The answer reveals a strange and subtle counterpart, a kind of anti-lens. When light from the cosmic microwave background or from distant galaxies must travel through one of these colossal supervoids, it encounters a landscape of profound gravitational lack. Instead of a deep well that severely curves spacetime, the void presents a gentle, almost flat plane. Light passing through this region experiences far less bending than it would traveling through an average patch of the universe. This lesser bending has a counterintuitive effect. While a massive cluster focuses light like a magnifying glass, making background objects appear larger and brighter, a supervoid does the opposite. It causes a slight demagnification. The light rays are bent away from each other just a fraction, making the ancient CMB light in that direction appear a tiny bit cooler and stretched, while the shapes of background galaxies are distorted in a specific, measurable pattern. This is the Rees-Simon effect, a subtle imprint of evolving cosmic structures on the light that passes through them. Detecting it is an extraordinary challenge, like trying to measure the shadow of a whisper. But for cosmologists, it is a direct window into the void's true nature. By measuring this anti-lensing effect, scientists can perform a remarkable feat. They can weigh the nothingness. They can calculate the total mass deficit of the void, the amount of matter that is missing compared to the cosmic average. This provides an independent, crucial test for our models. Does the amount of demagnification we observe match what the Lambda-CDM model predicts, given the void's observed size and the presumed influence of dark energy? Or does the shadow cast by the emptiness hint at a discrepancy? Each void becomes a natural laboratory where light itself is the probe, revealing the gravitational signature of absence. This reverse lensing confirms that emptiness is not inert. It is a dynamic feature with a gravitational profile we can map and measure. The silent void, it seems, still leaves a faint signature on the light that dares to cross it, a signature written in the language of missing gravity. Deep in the cosmic microwave background lies a ghostly chill that has puzzled astronomers for years. It is known simply as the cold spot, a region in the constellation Eridanus that is significantly colder than the surrounding afterglow of the Big Bang. This is not a minor fluctuation, but an anomaly so large and so cold that its probability of occurring by random chance in our standard model of the universe is less than 1 in 100. For a while, the most compelling explanation was not a flaw in the primordial universe, but a shadow cast much later by one of the largest structures we could imagine, or rather, fail to imagine. Researchers propose that between us and this patch of ancient light sits a truly colossal void, a supervoid of such immense scale and profound emptiness that its gravitational effect, the Integrated Sachs-Wolfe effect, could imprint this distinct cold signature on the CMB. They called it the Eridanus supervoid. The idea was elegant and powerful, a direct link between the largest emptiness in the nearby universe and the oldest light from the distant past. It would be a crowning validation of how these vast cosmic deserts actively sculpt the light traveling through them. The hunt for this phantom void began. Astronomers scoured galaxy surveys, mapping the distribution of matter in the direction of the cold spot. The initial findings were tantalizing. Some studies did report evidence of a significant underdensity, a large, sparse region that could fit the bill. The pieces seemed to be falling into place for a monumental discovery. Yet, as more powerful telescopes and deeper surveys examined the same patch of sky, the story grew murky. The problem is one of scale. To produce the observed depth of the cold spot through the Integrated Sachs-Wolfe effect, the proposed supervoid would need to be almost unbelievably large and empty, pushing the boundaries of what our cosmological models predict is even possible. Some subsequent, meticulous surveys have simply failed to find a void of the necessary gargantuan proportions. They find emptiness, yes, but not the legendary, universe-straining emptiness required to explain the anomaly. This leaves us with a fascinating cosmic detective story still very much unsolved. Is the Eridanus supervoid real but just beyond the current limits of our surveys, waiting to be fully mapped? Or is the cold spot a statistical fluke, a rare but possible random fluctuation in the primordial soup? Perhaps it is something else entirely, a signature of a more exotic physics from the universe's earliest moments. This ongoing controversy highlights a fundamental truth in modern cosmology. Connecting a specific anomaly in the ancient sky to a specific structure in the modern universe is incredibly difficult. It requires not just finding a void, but precisely measuring its size, its shape, its exact density profile, and untangling its effect from all the other structures the CMB light has passed through over 13 billion years. The case of the cold spot reminds us that the cosmos is a complex, layered puzzle. Even our most powerful tools and elegant theories can meet their match in the quiet, confounding depths of nothingness. The silent expansion of these voids is a clock ticking toward cosmic destiny. If dark energy continues to dominate, these vast bubbles of nothingness are not just features of the universe, they are its future. As the relentless push of dark energy accelerates, the delicate filaments of the cosmic web, already stretched thin, will begin to tear. Galaxies within those thinning threads will find their gravitational bonds overcome by the expanding space between them. Over trillions of years, the great metropolises of galaxy clusters will become isolated islands, and the islands themselves will grow dark as their stars burn out. The voids will merge and grow, their boundaries dissolving as the structures that define them are pulled apart. The end result could be a cosmos of profound, permanent solitude, where the distances between any remaining particles become so vast that no future observer could ever know another existed. This is the potential fate known as heat death, a universe expanding into a cold, dark, and uniform stillness. But voids offer us a way to test this prediction. By meticulously measuring how fast voids are growing today, cosmologists can take the temperature of dark energy. Is its strength constant, or is it changing over time? The answer determines whether our universe will fade gently into that long night or meet a more violent end. Some models suggest a dark energy that grows stronger, leading to a big rip scenario where even atoms and atomic nuclei are torn apart by the runaway expansion of space itself. The growth rate of voids is a direct measurement of dark energy's grip on the cosmos. A void that expands faster than our models predict could be the first clue that dark energy is not a gentle constant, but a force that evolves with terrifying implications for the far future. In this way, the emptiest places in the universe become our most powerful telescopes, not looking out across space, but forward across time. They hold within their evolving geometry a forecast for all of existence. By listening to the silence and measuring the pace of its spread, we are reading the final chapter of the cosmic story, written in the language of absence. The early universe was a roaring sea of sound. In its first few 100,000 years before the formation of any star or galaxy, the cosmos was a dense, hot plasma of particles and light constantly churning. Within that primordial soup, gravity tried to pull matter together into clumps, while the intense radiation pressure of the light pushed it apart. This tug-of-war created colossal spherical pressure waves, ripples that expanded outward through the fiery medium like sonic booms from a cosmic explosion. Then, in a single, defining moment, the universe cooled enough for atoms to form. Light suddenly broke free from matter, a flash we now see as the cosmic microwave background. At that instant, those pressure waves froze in place, leaving a permanent, ghostly imprint on the distribution of matter. We call this fossil imprint Baryon acoustic oscillations. It gave the universe a signature rhythm, a preferred scale woven into the fabric of everything to come. That scale is enormous, about 500 million light-years across. It manifests as a subtle statistical tendency for galaxies to be separated by that specific distance. But perhaps the clearest echo of this ancient sound is not found in the crowded places, but in the empty ones. The same pressure waves that pushed matter outward also left behind spherical shells of slightly higher density, and inside those shells, the seeds of the voids. This means the characteristic size of the cosmic voids we see today is not random. It is directly tied to the size of those frozen sound waves from the infancy of everything. That 500 million light-year scale is literally the radius of the bubbles that began to form when the music of creation stopped. This transforms the void from a mere curiosity into one of cosmology's most precise instruments, a standard ruler etched into the emptiness. Imagine you are an astronomer trying to measure how the universe has expanded over billions of years. You need a fixed reference, a ruler of known length that you can observe at different distances, and thus different epochs in the past. Galaxy clusters are messy, their shapes distorted by mergers and local gravity, but a void, especially a large spherical one, is a much cleaner object. Its growth is governed primarily by the smooth background expansion of the universe and the pull of dark energy. By surveying vast volumes of space and measuring the diameters of thousands of voids, scientists can look for that preferred size, the echo of the Baryon acoustic oscillations. They can ask, does this standard ruler appear longer or shorter when we look at voids in the distant, younger universe compared to voids nearby? Any stretching or compression of this ruler across cosmic time is a direct measurement of how space itself has expanded. The results are profound. Studies using voids as this standard ruler have independently confirmed the accelerating expansion of the universe. They tell us that the ruler appears stretched in the modern era compared to the past, meaning space has expanded more than our simple models of gravity would predict. The empty spaces, therefore, are not just expanding, they are preserving within their geometry the very history of that expansion. They offer a low-noise, high-precision alternative to other methods, cutting through the chaotic details of galaxy formation to reveal the smooth, underlying beat of cosmic growth. In the quiet of the void, we can still hear the faint, fading echo of the universe's first and only song, and by listening closely, we measure the force that is changing its tune. The sheer scale of a supervoid is a direct assault on human intuition. To comprehend the Boötes Void, picture our own galaxy, the Milky Way, a majestic spiral of several 100 billion stars, placed at the very center of that immense sphere of nothingness. From that lonely vantage point, our entire local group of galaxies, including the great Andromeda and dozens of smaller satellite galaxies, would occupy a region less than 1% of the void's diameter. It would be a faint, insignificant smudge of light in a cavern of staggering darkness. The next major cluster of galaxies, the nearest bustling metropolis in the cosmic web, would be tens of millions of light years away in every direction. You could travel for lifetimes at the speed of light and encounter nothing but a profound and unbroken silence. This is not a metaphor, it is the mathematical reality of these structures. They redefine what we mean by empty. This staggering emptiness does more than challenge our equations. It fundamentally reshapes our cosmic perspective. For all of human history, our view of the universe was built from points of light. We navigated by stars, told stories in constellations, and later discovered that those stars gathered into galaxies. We naturally assumed the cosmos was a place of things, of brilliant structures and bustling activity. The voids reveal this to be a profound illusion, a bias born from our fortunate location in a relatively dense neighborhood. The truth is the opposite. The bright, dense filaments and clusters where galaxies thrive are the rare exceptions, the tiny, glowing islands in a vast and dominant sea of nothing. Our familiar realm of stars, planets, and nebulae exists in what are essentially the universe's backwaters, the narrow ribbons of matter suspended within an overwhelming ocean of void. This realization is a quiet form of cosmic humility. It tells us that the universe is not primarily a place of light and structure, but of space and silence. The grand tapestry we marvel at is embroidery on a fabric of profound, expanding darkness. To understand the cosmos, then, we must learn to study the silence as intently as we study the song. Mapping emptiness is a paradox of subtraction. Astronomers cannot simply point a telescope at a dark patch of sky and declare it a void, for the apparent darkness might just be a local gap, a simple shadow in the foreground of a much richer cosmic neighborhood beyond. To truly identify one of these colossal structures, they must perform a meticulous three-dimensional census, pinpointing the precise locations of millions of galaxies to reveal the cavernous volumes where galaxies are conspicuously absent. This is the ultimate challenge of seeing what is not there. It demands surveys that can cover enormous swaths of the sky, capturing not just images but the faint fingerprints of light that reveal distance. Every galaxy's spectrum, the unique barcode of its chemical composition, is stretched toward the red end of the light spectrum by the expansion of the universe. The degree of this redshift tells us how far away the galaxy is, and thus how deep into the cosmic past we are looking. By collecting redshifts for millions of galaxies, astronomers can build a three-dimensional map of the universe's large-scale structure. The voids emerge as the great spherical bubbles in that map where the pinpricks of light simply vanish. But this process is fraught with difficulty. The galaxies that define the boundaries of a void are often incredibly faint and distant. Capturing their detailed spectra requires immense telescope time and sensitivity. Furthermore, to be statistically confident that a void is real and not just a random fluctuation, you need to map a volume of space so vast it boggles the mind. For decades, our maps have been like early cartography, revealing the continents of the cosmic web but leaving the interiors of the oceans largely blank, hinted at but not precisely charted. This is about to change in a revolutionary way. A new generation of astronomical observatories is coming online, engineered specifically to solve this problem. The Vera C. Rubin Observatory, with its gigantic mirror and camera the size of a small car, will scan the entire southern sky every few nights, not just once, but over and over for a decade. It will detect billions of galaxies, measuring their positions and shapes with exquisite precision. Alongside it, the Euclid Space Telescope, positioned in the quiet darkness beyond Earth's atmosphere, will peer even deeper, capturing the infrared light from galaxies so ancient their visible light has been stretched into invisibility. Together, these instruments will not just add more dots to our map, they will create a high-definition, volumetric portrait of the cosmos. They will trace the faintest filaments with clarity, and in doing so, will outline the voids with a sharpness we have never before achieved. We will move from knowing voids exist to understanding their intricate anatomy, their exact shapes, the steepness of their density walls, the distribution of the few lonely galaxies within them. This transformation is crucial. A fuzzy statistical blob of emptiness is interesting, but a finely detailed, three-dimensional structure is a laboratory. With this new data, cosmologists can perform rigorous experiments. They can measure how the shapes of voids align with the cosmic microwave background's cold spots, testing the Integrated Sachs-Wolfe effect with unprecedented rigor. They can track the peculiar velocities of border galaxies with far greater accuracy, weighing the gravitational influence of the unseen dark matter. They can use the voids as that pristine standard ruler from the universe's first sound waves, measuring cosmic expansion with a new level of confidence, free from the messy astrophysics of bright galaxies. In essence, these new telescopes are not just built to find more things. They are built to define the nothingness with such precision that the silence itself begins to speak in clear, testable predictions. The era of the void as a cosmic curiosity is ending, and the era of the void as a fundamental cosmological tool is just beginning. The profound emptiness of a void is more than just a cosmic oddity. It is a frontier of physics. Within these vast bubbles, the universe presents conditions so extreme they are impossible to create in any laboratory on Earth. Here, the density of matter is 1 billion times lower than in our galactic neighborhood, and the dominant force is not gravity, but the mysterious push of dark energy. This unique environment transforms each supervoid into a pristine natural laboratory, a testbed for probing the deepest mysteries of fundamental physics, even those that lie beyond our current standard model. For instance, consider the neutrino, one of the universe's most elusive particles. Trillions pass through your body every second, yet they interact with matter so rarely they are often called ghost particles. In the dense, crowded environment of a galaxy cluster, their subtle effects are drowned out by the roar of other processes, but inside a void, the background noise of the cosmos drops to a whisper. Some theories suggest that the collective behavior of these neutrinos, or even exotic new types of particles we have yet to discover, could have a tiny but measurable effect on how the void evolves and expands. Detecting such a signal would be like hearing a single pin drop in a silent cathedral, a feat only possible because of the profound quiet. Similarly, the nature of dark energy itself is the greatest puzzle in modern cosmology. Is it a constant energy woven into space, as Einstein once proposed, or is it a dynamic field that changes over time? The near-total vacuum of a supervoid, where dark energy's influence is magnified, is the perfect place to look for answers. If dark energy's strength varies even slightly, its fingerprint should be most visible in the precise growth rate of these empty regions. By measuring the expansion history encoded in thousands of voids, astronomers are not just charting emptiness, they are conducting a direct experiment on a force that governs the fate of everything. This pursuit, while speculative, highlights a profound truth about how science operates on the grandest scale. We cannot build a particle accelerator large enough to recreate the conditions of the early universe, nor can we construct a vacuum chamber the size of a supervoid. But we can use the cosmos itself as our experimental apparatus. The voids are a gift of nature, offering a set of physical conditions so clean and so extreme that they allow us to ask questions we could never ask in a lab. They push our theories to their limits, inviting us to look for the faintest cracks in our understanding. A discrepancy in a void's predicted size or the motion of its border galaxies could be the first whisper of a revolution, a hint of physics that operates only in the deepest silences of the universe. The silence of these cosmic voids speaks to something deeper than physics alone. It touches on questions humans have asked for millennia about our own smallness and the nature of a universe that seems indifferent to our existence. We are pattern-seeking creatures by nature, finding constellations in random stars and meaning in chaos. Yet the voids present a profound counterpoint to that instinct. They are not patterns of light, but patterns of absence woven into the very fabric of everything. Their existence forces us to confront a humbling truth. The universe is not built primarily for structure, but around emptiness. The luminous galaxies and glittering clusters we celebrate are the rare embellishments on a canvas of overwhelming dark. This realization carries a quiet, existential weight. For centuries, our philosophical and even spiritual frameworks often placed humanity, or life itself, at some kind of center. We imagined a cosmos that was, in some fundamental way, full, bustling, and perhaps even designed. The voids dismantle that notion completely. They show us a cosmos where vast stretches of nothingness are not accidents, but foundational features. These are places where the universe expresses its capacity for sheer, unadorned space, for scales of emptiness that utterly dwarf not just our planet, but the collective light of every civilization that could ever exist. In that sense, they are the ultimate cosmic deserts, landscapes defined not by what they contain, but by what they do not. They remind us that the cosmos operates on a logic of its own, under no obligation to be full, hospitable, or even fully comprehensible to the human mind. This is not a cause for despair, but for a deeper kind of wonder. It shifts the question from where do we fit in to what does it mean to exist within such a reality. The voids teach us that meaning is not something out there, waiting to be discovered in the architecture of the heavens. It is something we create and project from our unique vantage point within a tiny island of matter. Our search for understanding, our drive to map these immense silences, becomes its own answer, a testament to a consciousness that arose in the light, striving to comprehend the dark. The scientific pursuit itself gains a new layer. It is not just about cataloging what is, but about grappling with the profound reality of what is not. And in that grappling, we find a strange kinship with the emptiness, for it is the silent backdrop against which every story, including our own, becomes possible. Our own galaxy is not a detached observer of this cosmic emptiness. We are participants, living on the very edge of one of these vast structures. Surrounding our local group of galaxies, which includes the Milky Way and Andromeda, is a region of profound underdensity known as the local void. It is not as colossal as the Boötes Void, but it is immense by any human measure, stretching for hundreds of millions of light years in one direction. This isn't a distant abstraction, it is the gravitational neighborhood right outside our galactic door. For a long time, its influence was subtle, hidden within the complex motions of nearby galaxies. But recent, precise mapping has revealed its gentle push. You see, everything in our corner of the cosmos is in motion, pulled by the immense gravity of the nearest giant concentration of matter, the Virgo cluster, which anchors a supercluster of galaxies we are part of. Yet, when astronomers calculated the expected pull from Virgo, they found our local group was moving slightly faster than it should be. Something else was giving us an extra nudge. The culprit appears to be the local void itself. With so little matter inside it, the void creates a gravitational imbalance. The denser regions on the opposite side of us, like the Virgo cluster, pull us toward them with a stronger force than the near vacuum of the local void can pull us back. The net effect is that the emptiness behind us is not holding us back, effectively adding to our speed toward the cosmic metropolis. This subtle contribution is part of what astronomers call our peculiar velocity, the specific way our galaxy deviates from the smooth Hubble flow of universal expansion. It means the silent, expansive nothingness that begins not far from our galactic borders is actively helping to set our course through the cosmos. This personal connection transforms the mystery from a distant curiosity into a tangible part of our existence. The same forces that sculpt the billion light-year bubbles of the cosmic web are at work here in our own backyard, gently shepherding our island of stars through an ocean of dark. It is a humbling reminder that we are not just looking at the cosmic web, we are embedded within it, our path quietly guided by both the presence of great masses and the profound absence that lies just beyond our sight. This cosmic desert did not simply appear, it was born and grew. Every colossal void we see today began its existence as the faintest of whispers, a region in the newborn universe that had just a fraction less matter than its surroundings. In that searing, dense early cosmos, this tiny underdensity was almost insignificant, a quantum hiccup in an otherwise smooth sea of hot plasma, but it was a seed of future emptiness. As the universe expanded and cooled, gravity began its slow, relentless work. It pulled matter toward the slightly denser regions, which grew into the filaments and clusters of the cosmic web. Meanwhile, that initial underdense patch experienced the opposite fate. With less gravitational pull to hold it together, it expanded slightly faster than the cosmic average. This faster expansion made it even emptier relative to its surroundings, which in turn caused it to expand even faster. A powerful feedback loop was set in motion, a runaway process of self-reinforcing evacuation. Over hundreds of millions of years, this gentle dimple inflated into a recognizable bubble within the growing cosmic sponge. But a void does not grow in isolation. Just as galaxies collide and merge to form larger galaxies, voids too undergo cosmic mergers. Smaller neighboring voids, born from their own underdense seeds, expand until their boundaries touch. When they meet, the thin wall of matter separating them is stretched and torn apart by their combined expansion. The two empty regions flow together, merging into a single, larger, and more spherical void. This hierarchical growth is a fundamental part of their life cycle. Through countless mergers over billions of years, a mature supervoid like the one in Boötes is formed, a vast cavern carved out by the collective drainage of matter toward the luminous web around it. This life cycle gives voids a predictable evolution, a kind of biography we can trace. In their youth, they are smaller and more irregular, actively draining matter and merging with neighbors. In their mature phase, they become vast, stable, and remarkably spherical, their growth slowing as they reach equilibrium with the gravitational pull of the dense walls that cage them. But what of their old age? The future of a void is dictated by the ultimate victor in the cosmic tug of war. If dark energy continues to accelerate the universe's expansion, as all evidence suggests, a new phase will begin. The dense filaments and walls that define the void's boundaries will themselves be stretched and diluted by the accelerating space. The void will stop actively merging because the structures it would merge with will be ripped away, receding faster than the void itself can expand. In this late era, each supervoid will become an isolated island of accelerating nothingness, expanding in perfect, silent isolation. The cosmic web will be shredded, its threads severed by the relentless stretch of space. The voids will not conquer the universe, they will become the universe as all structure fades into a uniform, cold, and dark expanse. Understanding this full life cycle, from quantum seed to merging adolescent to mature supervoid and finally to isolated relic, is what transforms these empty regions into precise cosmological tools. By counting voids at different stages of growth, we can read the expansion history of the universe like rings in a tree trunk. Their merger rate tells us about the strength of gravity and the density of dark matter. Their ultimate fate is written in the strength of dark energy. They are not static wholes but dynamic characters in the cosmic story, each phase of their existence offering a new clue to the forces that sculpt everything. The next generation of cosmic cartography is already on the launch pad, equipped with tools designed to map the silence. NASA and Nancy Grace Roman Space Telescope and the European Space Agency's Euclid mission represent a fundamental shift in our approach. These are not telescopes built merely to find new stars or photograph distant planets. They are cosmological instruments engineered to survey the structure of the universe itself, with the colossal voids as a primary target. Their strategy is one of overwhelming precision and scale. Imagine trying to understand the shape of a giant, dark cave by only seeing the flicker of a few lanterns near its entrance. That has been our limitation. These new observatories will instead flood the cavern with light. They will perform what astronomers call ultra-deep, wide-field surveys, capturing the positions, shapes, and distances of billions of galaxies across an immense volume of the cosmos. This is the difference between a sketch and a high-definition three-dimensional scan. For the first time, we will not just know voids exist, we will see their anatomy in exquisite detail. We will be able to trace the subtle gradients of their near-vacuum interiors, measure the exact steepness of their dense boundary walls, and count every single, lonely galaxy that drifts within them. This data is the raw material for a revolution. By combining multiple lines of evidence, the weak gravitational lensing that shows how void shapes distort background light, the precise clustering of galaxies that defines their edges, and the shadows they cast on the cosmic microwave background, these missions will perform a cosmic autopsy on emptiness. They will measure with unprecedented accuracy the gravitational tug of war happening within these realms. Is the expansion rate inside a void exactly what our standard model predicts given the local lack of matter and the presumed strength of dark energy? Or is there a tiny, telling discrepancy? A slight mismatch in the data could be the first whisper of something profound, a hint that gravity behaves in an unexpected way in the most extreme underdensities, or that dark energy is more complex than a simple constant. These empty spaces, once seen as barren, are about to become the universe's most stringent proving grounds. The answers we find there will not just solve the mystery of the voids, they will rigorously test the very laws we believe govern all of reality, potentially uncovering new physics in the last place we might have thought to look, the profound and silent nothing between the stars. The most radical explanation for these voids does not come from within our universe, but from outside it. We have explored how emptiness is sculpted by dark energy and dark matter, forces that operate within the cosmic rules we know. Yet a handful of theoretical cosmologists look at the largest, most peculiar voids and ask a question that borders on metaphysics. What if these are not just empty spaces, but cosmic scars, evidence of a reality far larger than our own? This idea emerges from the most speculative models of a multiverse. In this framework, our entire observable cosmos, with all its galaxies and voids, is not the totality of existence. It is merely one bubble in an infinite, frothing sea of eternally inflating space, a single soap suds in a cosmic sink. Other bubbles, other entire universes with their own laws of physics, could be constantly forming and expanding in this greater beyond. The theory suggests that if our bubble universe had a violent birth, brushing against a neighboring bubble in that primordial foam, the collision could have left a permanent bruise on the fabric of our reality. What would such a bruise look like? Some calculations suggest it could manifest as a vast, spherical region of unusual properties, a place where the density of matter is dramatically lower, or the cosmic microwave background shows a strange, coherent pattern of cold. In essence, it could look remarkably like one of our colossal supervoids, or align with an anomaly like the cold spot. The sheer scale and apparent isolation of the largest voids are what keep this exotic idea alive in the minds of some theorists. A void that seems too large, too empty, or too perfectly spherical within the standard model of cosmic evolution becomes a candidate for something more, a fossil imprint from a time before our universe was alone. It is crucial to state clearly that there is no direct evidence linking any known void to a bubble collision. The standard explanations involving dark energy and gravitational drainage remain far more likely and are supported by a mountain of data. This multiverse hypothesis exists on the farthest frontier of science, where testable predictions are incredibly difficult to formulate, and the line between cosmology and philosophy grows thin. Yet, its enduring appeal lies in what it represents: the ultimate human drive to explain the origin of structure itself. We look at the great cosmic desert and ask not just how it formed, but why it is here at all. Could its origin story be written not in the first moments of our Big Bang, but in an encounter with another universe entirely? To even entertain the question reframes our entire pursuit. Mapping the voids then becomes more than charting emptiness. It becomes a search for fingerprints on the very walls of our cosmic bubble, a hunt for clues that we are part of something incomprehensibly vast. These isolated islands of light within the void are not just stragglers, they are unique cosmic specimens. In the deep gravitational valleys of a supervoid, far from the bustling crowds of galaxy clusters, a handful of galaxies manage to form and persist. Astronomers call them void galaxies, and they are the hermits of the cosmos, evolving in profound solitude. Their existence alone is a puzzle, as the sparse gas in these regions should struggle to collapse under its own gravity. Yet, against the odds, stars are born in the desert, free from the violent gravitational tides and frequent collisions that define life in a dense cluster. Void galaxies follow a different evolutionary path. They tend to be smaller, often taking on irregular, delicate shapes like lonely, spinning pinwheels adrift in the dark. Without the constant gravitational harassment from massive neighbors, they are not stretched and twisted into the classic spiral or elliptical forms we see elsewhere. Their color is another telltale sign, a distinctive, youthful blue. This hue comes from an abundance of hot, young stars, suggesting that in their quiet isolation, the gas they do possess can form new stars in a more steady, less chaotic fashion. It is a slower, more contemplative pace of cosmic life. This makes each void galaxy a pristine natural laboratory. In the crowded urban centers of galaxy clusters, a galaxy's evolution is dominated by its environment, shaped by gravitational encounters, collisions, and the stripping away of its gas by the hot plasma that fills those regions. It is a tumultuous, externally driven existence, but a void galaxy is an introvert. Its growth and changes are driven almost entirely by its own internal processes, the slow consumption of its gas reserves, and the gentle feedback from its own supernova. By studying these isolated systems, astronomers can isolate the intrinsic recipe for galaxy evolution, understanding what a galaxy does when it is left entirely to its own devices. Their very presence, however, deepens the mystery of the voids themselves. How did these galaxies form in places where the gravitational anchor is so weak? The leading theory suggests they are ancient relics, the sole survivors of a gentler era. They may have formed very early on from small, initial overdensities that were just strong enough to hold onto their gas while the great cosmic drainage occurred around them. As the void expanded and emptied, these galaxies were left behind, like the last trees standing in a vast, cleared field. Their ongoing, quiet star formation is a testament to their ability to hoard and carefully use their limited resources over billions of years. Studying these stellar hermits gives us more than just a picture of galactic solitude. It provides a crucial baseline for understanding how environment dictates destiny across the cosmos, from the quietest deserts to the most chaotic metropolises. All these threads of evidence weave together into a single, coherent picture of the cosmos. The integrated Sachs-Wolfe effect, the peculiar velocities of border galaxies, the subtle anti-lensing, the supercomputer simulations, and the pervasive influence of dark energy are not separate clues. They are different observations of the same grand, dynamic process. The illusion of repulsive gravity within these colossal voids is not a sign of broken physics, but a profound testament to how gravity behaves when matter is almost entirely absent and the fabric of space itself is stretching at an accelerating rate. Here is the narrative stripped of its mystery. Gravity has not reversed. It is still pulling, exactly as Einstein's theory dictates. The void is a region of profound matter deficit, a gravitational landscape that is almost flat. The dense walls and filaments surrounding it are regions of immense matter surplus, creating deep gravitational wells. A galaxy on the boundary feels a much stronger pull from the massive wall behind it than any feeble tug from the emptiness ahead. This net force draws it toward the dense structure, which from our vantage point looks exactly like a push away from the void. That is the first layer of the illusion, a simple matter of gravitational contrast. But there is a second, crucial actor amplifying this effect, the decay of the gravitational potential itself. In a static universe, this contrast would be stable. Yet our universe is not static, it is accelerating, driven by dark energy. Over cosmic time, as the void expands and empties further, its already shallow gravitational well becomes even shallower. The deep wells of the surrounding clusters also decay slightly. This change in the gravitational landscape over time is what produces the observable signatures, the hot and cold spots in the ancient light, and the organized flow of the border galaxies. The combined result is a dynamic where the emptiness seems to actively repel matter, not because it is pushing, but because everything else is pulling harder, and the space within the void is stretching more aggressively, carrying the floor away. The backward gravity is thus a powerful cosmic sleight of hand. It reveals that our intuitive, local experience of gravity as a simple, attractive force between objects is a special case, a rule that applies within our dense galactic neighborhood. On the largest scales, where the dominant forces are the smooth distribution of dark matter and the relentless pressure of dark energy, gravity's story becomes one of evolving landscapes and competing influences. The voids are the stages where this grander, more complex performance is most clearly visible. They teach us that to understand the universe, we must sometimes learn to trust the equations over our instincts, to see the pull hidden within the apparent push, and to recognize that the greatest mysteries often lie not in what is present, but in how we interpret the profound and shaping power of absence. The silence of these cosmic voids, then, is not an endpoint but a beginning. While we have unraveled the grand illusion of repulsive gravity and mapped the anatomy of emptiness, the deepest questions are the ones that remain unanswered, the puzzles that keep cosmologists awake at night. For every mystery solved, a new, more subtle one emerges from the data. Take the enigmatic cold spot in the cosmic microwave background, that chilling anomaly in Eridanus. The debate is far from settled. Is it the definitive shadow of an immense, yet to be fully mapped supervoid, a structure so vast it strains our models? Or is it simply a rare but possible statistical fluctuation, a random cold patch in the primordial fire's fading glow? Each new, deeper galaxy survey brings conflicting clues, and until we can precisely weigh the nothingness in that specific direction, this ghostly chill will haunt our maps of the early universe. Equally perplexing are the precise motions of galaxies on the borders of these voids. Their peculiar velocities, those subtle streams away from the emptiness, are a critical test. Do they match the predictions of our standard Lambda-CDM model with perfect precision? Or do they contain a tiny, persistent wiggle, a hint that gravity itself might need a subtle tweak in these most extreme underdensities? The measurements are at the very edge of our observational capabilities, and the slightest discrepancy here could be the first crack in a foundational pillar of physics, pointing toward a modified theory of gravity or a new type of particle influencing the cosmic dance. Perhaps the most pressing puzzle is the intimate link between void properties and the nature of dark energy itself. Cosmologists describe dark energy with an equation of state, a number that defines its pressure and density. Is this number a constant, unchanging for all time, as the simplest model suggests, or does it vary, evolving as the universe ages? The growth rate of colossal voids, their sizes and distributions across cosmic time, are exquisitely sensitive to this very number. By measuring how voids have expanded over the past 10 billion years, we are essentially taking dark energy's temperature across cosmic epochs. Any deviation from the expected pattern would signal that dark energy is not a static background force but a dynamic entity, with profound and startling implications for the ultimate fate of all things. These open questions are not signs of failure, but of a vibrant, living science. They are the engines that drive the field forward, ensuring that these colossal voids will remain at the very center of cosmological research for decades to come. They challenge our most cherished models, beckoning us to look deeper, map more precisely, and think more creatively. In their profound silence, the voids hold the keys to the next revolution in our understanding, guarding the secrets of gravity, dark energy, and the hidden architecture of everything. Our journey through these silent expanses has been a voyage into the negative space of creation. We have traced the outlines of emptiness and found it to be filled with meaning, a dynamic force sculpted by the same gravity that builds the galaxies. These colossal voids are not cosmic accidents. They are the inevitable and profound shadows cast by the construction of everything we see. They challenge our intuition, presenting the powerful illusion of repulsive gravity, not because the laws of physics are broken, but because they are operating on a stage of unimaginable scale and subtlety. That apparent push is the signature of a grand cosmic contrast, where the strong pull from surrounding walls of matter, combined with the accelerated expansion of space within the void itself, creates a river of galaxies flowing away from the emptiness. In their profound quiet, these voids have become our most precise instruments. They are natural laboratories where we test the very fabric of reality, weighing the influence of dark energy, probing the nature of gravity in its weakest state, and listening for echoes of the universe's first sound. They remind us that to understand the cosmos, we must learn to study the silence as intently as we study the light. The universe is not primarily a place of brilliant structure, but a vast and evolving tapestry where emptiness is the canvas and the luminous galaxies are the rare, delicate threads. This perspective is a gift of cosmic humility, reshaping our view from one centered on islands of matter to one that embraces the dominant, silent ocean in which they float. If this exploration has pulled your curiosity toward the mysteries written in absence, we would love to hear which void phenomenon fascinated you most. Share your thoughts in the comments below and subscribe to join us as we continue to map the unseen architecture of everything.